Hello there and welcome to this video series on control systems. We can give a quick review of what we have seen so far as given here. We have defined the Laplace transform by this equation. We use lowercase letters for time domain functions, corresponding uppercase letters for Laplace domain variables. We have defined and derived Laplace transforms of several standard functions and explored the properties of Laplace transforms. After watching this video, you will be able to specify what is inverse transform and find inverse transforms of several simple functions. From the teacher's side, this video is very short and brief, but I guess for a student this is kind of heavy groundwork, mathematical groundwork in Laplace transforms required for further topics in control systems. So I strongly advise you to spend at least 2 hours in going through the matter over and over again, deriving each equation, transform, inverse transform on your own, and convince yourself that all this is correct. With that, let us begin the video by defining what we mean by inverse transform. This inverse Laplace transform is something similar to what we say in trigonometry: sine inverse, cosine inverse, and so on. If capital F of S is the Laplace transform of f of t, then this time domain function may be termed as inverse transform of f of S. So this f of S and f of t form a pair. One is the Laplace transform and the other is the inverse transform. Fs is the Laplace transform, ft is the inverse Laplace transform, and we represent that fact by this equation or this equation as well. Think of that. I would strongly advise that you remember the table given in the subsequent slides. With that, we'll quickly go over the table of transforms and close this video. You have a unit step input for which the transform is 1 over s. So if you see any term involving lone s, you be sure that there is a unit step input. Whenever an exponential in time domain is involved, you have s minus alpha, where e power alpha t is the term. Similarly, whenever you have terms of the form s square plus a square, be sure that there is a sine term or cosine term. In the case of cosine term, there is a s here. Similarly, if you have terms involving s square plus a square whole square, you can be sure that there is a t cos at or t sin at. Similarly, when you have s square minus a square, you have sine hyperbolic or cos hyperbolic. If you see terms is something like s minus a whole square plus b square, you can be sure that there is a term e power at sin bt or e power at cos bt. These are some of the properties or facts that you can use to evaluate Laplace transform for other functions. For example, you have terms such as sin 3t or cos 4t or some f of alpha times or beta times t. You can use this to evaluate the Laplace transform very quick. If you have a time delayed function u of t minus c, you have e power minus cs. If you have integral, as in the case of a capacitor or sometimes as or a spring, something similar to that, where it stores energy, you have integral term. When you have integral, you have a s in the numerator. Similarly, when you have a derivative, nth derivative, this is slightly confusing, but if you expand it by substituting I is equal to 0, I is equal to 1, so on up to n minus 1, you can see that there are total n terms here. Okay, it takes a little bit of time. And then whenever you have e power alpha t, you substitute s minus a in place of s. This integral again is convolution integral. Okay, read about convolution integral and understand why it is used and so on. That will be very helpful. With that, I can give a summary as Laplace transform and inverse Laplace transform. They form a pair, and when you are trying to solve Laplace transform to solve differential equation, inverse transform forms a step in using Laplace transforms. And go beyond this lesson only if you derive all the equations given in the tables above, because that will ensure that you go through the subsequent lessons like a piece of cake. That's all we have for now. Have a great day.